Greetings. My name is Howard Chorney. I'm a member of the Shunra Performance Engineering team. And today I'd like to talk to you about Shunra's Performance Engineering Basics Application Principles module. To start, let's think about the difference a wide area network makes over a local area network. Let's also compound that by thinking about running different types of applications over a wide area network. Consider we have three users. We have a user in Tokyo, a user in London, and a user in New York. Let's look at our user in Tokyo. Our user in Tokyo will be accessing three different types of applications over a wide area network. That network would be the same link, the same line, and probably going through the same path. Let's ask a question. Will those applications behave the same way over the wide area network? The answer is no. Albeit they're going over the same link and the same distances, not all applications are engineered the same. What we're going to do today is examine a couple of principles of how an application being developed to work over a wide area network can affect the way the application works over the wide area network. What I'd like to do is talk about two of those main principles or characteristics. One being application turns, also known as application chattiness. The other being application transaction size. So, when data is transmitted over a wire, it is transmitted in streams of packets. And there are multiple packet streams per transaction in an application. Let's take this as an example. We have a user, and that user is doing a login. When that user does a login, that user is logging into a server. That server is going to authenticate a user. Now, when we log in, basically what are we doing? We're presenting our credentials to log in. So usually we're doing a username, password, then we're hitting a carriage return. When we hit that carriage return, many things are happening on the wire or under the covers that we don't see. And those things are called APE turns. If we look at a TCP transmission, what happens the first time we start to initiate a TCP transaction or transmission? Well, the first thing that's going to happen is our host is going to synchronize with our server by sending a SYN request. Our server is then going to acknowledge our client by sending something called a SYN ACK, where what it's doing is it's synchronizing with the host, between the server and the host, they're synchronizing, and it's acknowledging the synchronization. From there, the host is going to re-acknowledge with the server and send an ACK. That's called the three-way handshake. Now, in this three-way handshake, there are already three turns that have happened under the covers, so to speak, just on that one carriage return, and we haven't even started to do anything else yet. Think about if you're doing authentication and then you are downloading your profile remotely. What's going to happen is after we acknowledge, there could be other turns going on, passing streams of data from the server to our client. Again, you would only see this happening with one carriage return, yet it's all happening under the covers. These are called APE turns, and the more of these turns that you see, the more chatty the application. Now, on top of these turns, there's also something called payload size. Payload size is how many bytes are actually being sent over in a turn. And you can have as little as 1 byte to several thousand kilobytes. The larger the transaction, obviously the longer it's going to take to get from point A to point B. Also, the longer the distance between point A and point B, latency would play a factor in there too. So let's take a quick look here. This is called a transaction efficiency metric. This actually goes and looks at transactions side by side and looks at the characteristics of each transaction as it's happened over different distances. As we see here, we have a local user accessing his server locally, and it's doing a set of transactions, and we have a user 70 milliseconds of latency away from the server accessing the same transaction. Now we'll notice, obviously, they're probably not going to be the same transaction response time. So let's look at a couple of transactions in particular that we're going to to highlight that seem to be troublesome here. The first transaction I'm going to discuss is the OC underscore data entry O2 connect to database. Notice our local user will actually complete that transaction in 8.5 seconds. However, that remote user, going over 70 milliseconds worth of latency, will take 65 seconds to complete that same transaction. By looking at this chart, it will actually help us understand why that's happening. So the first thing we're going to do is look at application turns. You'll notice from our chart we have 34 application turns. One could argue if that were a lot of turns or not. I would say it's probably not an inordinate amount of application turns for a single transaction. What is remarkable about this is that if you look at the payload size, or how many kilobytes are in this transaction, it's over 5,600 kilobytes worth of data are being passed in this transaction. Therefore, basically, you're passing a freight train versus a speedboat worth of data over your line. So in this case, payload size is definitely the cause of why it took so much longer to go between our local user and our remote user. Let's look at the next transaction, which is OC data entry underscore 08. So let's see, we've gone from 2.33 seconds from the local user to over 14 seconds for our remote user. Well, let's look at our payload size. Looking at the payload size, I would say 75.9 kilobytes worth of data is not a lot. However, let's look at our application turns. In this case, we're going over 146 application turns to do this transaction. So 146 back and forths per transaction. Hence, that's why it's taking so long. So you can see here that the combination of one or the other can definitely adversely affect transaction response time. So how do we know what the best thing to do or tune? Let's say we did some testing and we found this out. What's the basic theory on what's going to be good and what's not going to be good? How do we know what is primed to tune and what's going to be better than others? Let's draw this graphically. We'll make one axis turns, the other axis payload size. What do we think would be the optimal size in turns to get data through quickly? If you guess 0, 0, it's probably pretty funny, but basically you're right. No data with no turns would absolutely be the fastest, right? So let's dispel a misnomer now. Let's think about this. Let's say we wanted all our transactions or all our payload to be 1 meg. And let's say we have to get 75 KB worth of data across the line. If 0, 0 is the optimal, and we're going to say transaction sizes are now going to be 1 KB, but we have to send 75 of those over the wire. If we chart this graphically, that means we're going to be out over here. Well, let's look at this for a minute. Now we have to send 75 app turns of this 1 KB. Imagine doing this over 70 milliseconds worth of latency. Now we're going to have this thing go across the wire 75 times. I don't think that's going to be very efficient. So let's look at this in the other direction. So what we're going to do is we're going to send 1 turn. We're going to go 1 turn, but we're going to send 1,000 KB worth of data. Once again, we're on the other side of the spectrum, right? So we have 1 turn, but over this 1 turn, we're sending 2 freight trains connected together, so to speak. A lot of data to move, albeit it's only once. Optimally, what we'd like to do is try and tune our turns in our payload to get more towards the center line. And yes, it would be a matter of experimentation as far as sending it over, but we'd want to try and average it a little more to get it into a little bit more reasonable time over reasonable turns. That will definitely help us tune the application. So hopefully you can see how things on one extreme versus the other extreme aren't going to help things, but we're going to have to kind of tune it in. And hopefully you can see how both turns and size affect data transmission. Next thing I'd like to talk about are visual ways that we can tell if there are application issues happening. These are pretty easy to develop, and they're very valuable, and will give you lots of information to help you make recommendations. So let's look at our first thing, which is called the latency scalability factor. Let's think about this for a minute. If we go back to our first example, we knew we had a user in New York City, we had a user in Tokyo, we had a user in London. They were all accessing different applications, but let's look at it from a single application for a minute. This is a matter of how we test to understand what our issues could be and how this application chattiness and payload size can really affect what our end users are going to see. Let's talk about our latency scalability factor. So what we're really trying to do now is we're trying to figure out how our remote users are going to act. We're going to figure this out from a single to a multi-site. We're going to look at local, regional, and global pieces. So what do we want to identify in this performance range? Or how are things going to act? Well, it all depends. Again, your application is going to act differently in different sites. It's actually going to act differently in different transaction sizes. And believe it or not, the time of day will also affect how your application will perform over the wide area network. This is a remote site performance range. You'll notice what we've done in this particular example. We have 7 different locations using 6 different types of transactions. We've also taken this and we've done it under 3 different types of conditions. That's network conditions. We did it under a best case condition. Best case defined as minimal traffic. You know, if we were to put it in a time frame, maybe 3 in the morning when there isn't a lot of things going on. Looked at it under worst case traffic. Worst case, what could that mean? 8:30 in the morning, everyone's logging in, or maybe 2 in the afternoon, the accounting team runs their special report, which puts a lot of information on the line at once. And then average case, what we'll see going across the day, non-peak times. So we'll see here we can definitely establish patterns, and we can take this information and pass it on to our development group. Or for developers, we can react on this and try and understand what's going on. Next thing we'd like to do is look at a performance curve. What this performance curve is indicating is that different types of applications will behave differently over the same network under similar network conditions. What we have here are basically 3 types of traffic that will go over a network. And you'll see each one of these types of traffic are affected differently, not only with latency and by latency, but percentage of how much time they're going to take due to that latency. So let's look at our first transaction, which is just basic internet browsing. You'll see over internet browsing that there's definitely a difference between 0 milliseconds or minimally 1 millisecond versus a user who's 70 milliseconds away. But since there isn't a lot of interaction going on here, again, it's a simple browse, that percentage delta isn't really that different between minimal latency and 70 milliseconds worth of latency. Now let's take a more interactive type of transaction. Maybe your company has an internet portal, and that portal is where you manage your benefits or just do things that you do every day from a corporate perspective. You'll notice there's a lot more interaction going on between you, the user, and whatever's happening on the web page. And again, you'll notice that the user who's local will be able to accomplish his tasks much quicker than a user who's remote. Again, there's an increase here. The percentage increase is going to be greater than the browsing, and could definitely adversely affect your user who's 70 milliseconds away. Now let's look at another type, a very interactive type of transaction that can happen over the web, and that would be like document content management. This is going to be very I/O intensive. There's going to be a lot of activity going on over the network. And again, you'll notice the local user will be quicker, but the remote user at 70 milliseconds is up to almost a minute to complete that transaction. So the more going on with the application, the longer the transaction response time will take. I really wanted to put this in here to highlight that fact. So the type of application you're using will definitely affect your transaction response time. This is kind of interesting. If we go back again and look at this and really concentrate on the different types of transactions, how do we know what's tying up? Where are we lagging? Where are we hanging? Where is the bottleneck? There's a way we can tell that. We can identify that with this front-end bottleneck client-server network breakdown. You'll see here in this particular graph that everything in blue is happening on the client side. everything in green is actually happening across the network. And that little itty bitty piece is actually what's happening on the server when it's going through its data. So in this particular transaction, we can see that 21% of this transaction is spent processing on the client side. 0.5% is actually spent processing on the server side. So what this would tell me is really serving the data out from the server side is nil. There is some action crunching going on the client side, but our main bottleneck is happening over the network. And by looking at all those factors we spoke about before, it will help us try and figure out why our bottleneck's going on in this particular transaction at the network level. Here's one more thing I'd like to point out in this module. This is a really good representation of watching a video or using streaming video on a client from a server. We'll notice on this video that to render the video locally, it took less than 10 seconds. As we increase latency, the amount of time it takes to serve the video moves exponentially. The reason I point this out is for this. When testing for something like this, it's much easier to get results using an emulation solution versus a simulation solution. What do I mean by that? A simulation solution is mathematically based. You need to write an equation to mathematically simulate your results. You're still not testing it for real. You're making an assumption that you've properly written your equation to get your results. From a Shunra perspective, an emulated solution actually allows you to apply the parameters and physically test that application against those parameters, achieving real-time data. Very much an advantage. Mathematical simulation, you have to develop the equation, put your parameters in. Could take days to do it. Doing simulation, again, can be very effective, but you have to make sure you have the right equation. Now, being an engineer, I do have some math skills, but I contend that it would take me quite a while to come up with this conclusion, if I could at all, depending on the quality of my equation, versus using an emulated solution such as Shunra, where I can physically witness the results, as we see here. So definitely a stronger way to find issues is using an emulated solution. So just to review this module, we looked at transaction size, we looked at application turns, we discussed how best to tune them, we've looked at different curves to show us how to get information, and we've discussed the difference between simulating application response time versus emulating application response time. Thank you very much.